filtering. Homomorphic filtering, it may use of the two terms. First is the illumination and second is the reflectance. The light falling on the object is called as an illumination, and light reflected from object is called as an reflectance. Then this is an object, light is falling of an object is called as an illumination, and light is reflected from an object is called as an reflectance. The key approach of homomorphic filtering is to separate illumination and reflection component. This homomorphic filtering key approach is separated from the illumination and reflected component. This homomorphic filter, which controls the both high frequency and low frequency components, are sometimes called as a homomorphic filter. This homomorphic filterings which control homomorphic filtering with high frequency and low frequency component called as a homomorphic filtering. This illumination are control the low frequency and illumination control the low frequency and reflection control the high frequency. Then homomorphic filter is sometimes used for the image enhancement. This homomorphic filter is used for the image enhancement, and it simultaneously normalizes the brightness. It normalizes the brightness of an image and increase the contrast. This homomorphic filter is increase the contrast of an image and normalize the brightness. Then f of xy is an image, and there are the may form the two terms, illumination and reflection. F of xy is equal to I of xy into R of xy. I of xy is equal to illumination and R of xy is a reflectance. This equation cannot be used directly to the operate on this frequency component of illumination and reflection, because the Fourier transform of product is not a product of the transform. This Fourier transformation of f of xy is not used or is not equal to Fourier transformation of I of xy into Fourier transformation R of xy. This term is used in plus, then is operate directly, but this term is not used in plus sign, this is into, it's not use apply. This cannot be used directly to the operate frequency domain component illumination and reflection, because there is a, this is not equal to the in this term. To separate the illumination and reflection component, we can use the natural logarithm. So z of xy is equal to apply natural logarithm of f of xy. Then f of xy is illumination of xy and apply logarithmic of ixy plus logarithmic of r of xy. This equation is 3. This equation is 1, equation 2, and this equation is 3. We now take the Fourier transform into the frequency domain. Then Fourier transformation of z of xy is equal to Fourier transformation of natural logarithm of f of xy. The value of natural logarithm f of xy is this. This value is put in this. Then logarithmic of I of xy plus logarithm of r of xy. This equation is 4. Or frequency domain z of uv is equal to fi uv plus fi uv. This equation is 5. Where fi uv, this fi uv, its term or its value is this value, logarithmic r of xy, and fr uv is a Fourier transformation of log of r of xy. This term is equal to this, and this term is equal to this. We now use the filter, homomorphic filter of uv. Then s of uv is equal to homomorphic filter into z of uv. This z of uv into the homomorphic filter, multiply by homomorphic filter in both side. Homomorphic filter h of uv into z of uv value fi uv plus apply multiply by homomorphic filter into z of uv. Z of one value is multiply and second value is fr uv. Then so this equation is a h of homomorphic filter. Then h of uv is a homomorphic filter.